Those Space People, a podcast series of casual cosmic conversations with people working on exciting space projects. Welcome to Thermal Lens, a special series focusing on thermal remote sensing, created by me, your host Rachana Mamidi, Agnieszka Sojinska, and Jennifer Susan Adams. Agnieszka is currently a research associate at the University of Leicester in the UK and has been working in the area of thermal remote sensing since 2017. Jennifer is a postdoctoral researcher at the University of Zurich in Switzerland and is currently focusing on measuring land surface temperature over forests. Agnieszka and Jennifer are also chairpersons of the Thermal Remote Sensing Special Interest Group of EARCEL, the European Association of Remote Sensing Laboratories. This group aims to bring together all the relevant stakeholders and provides a communication platform in the form of workshops, special sessions, seminars, and more. Welcome back to the second installment of our discussion with Ellis Friedman, the founder of Serious Science. In the previous episode, Ellis talked about the differences between large agency missions and smaller new space missions. In today's episode, we're going to deep dive into the finer aspects of thermal mission design with Ellis Friedman.
Can you think about any challenge specific to thermal satellites?
Well, yeah, there are some. I don't want to say that there are problems with thermal remote sensing. In some cases, thermal remote sensing is not that difficult. It depends upon the mission and what you're using. For example, for some small systems, not even that small, people are choosing to use what are called uncooled microbolometers. I don't know if your audience is familiar with microbolometers, but they are not what we would call photonic devices. They don't act uh, like solar cells. They don't turn photons into electrons that can be read electronically. They are tiny devices that change temperature, and when the temperature changes, their resistance to current changes, and that's how they estimate temperature. The nice thing is they don't require any cooling the way other infrared systems do. Microbolometers are very inexpensive right now. They have been for a while. They have their limitations, but they're fairly easy to use, and they don't require much more than what you would find in visible systems. But they do have their limitations in terms of noise, in terms of response. Other IR systems do have challenges. All the others have to be cooled with some kind of onboard cooling, whether it's passive cooling, where you have what's called a passive radiator that radiates out toward deep space to keep things cool. That's what Landsat does, or did. Um, and you can use what's called a cryocooler. Cryocoolers uh, are basically refrigerators or freezers. They keep the temperature low, but in some cases they vibrate, and the vibrations can be transmitted to the focal plane or the camera, which causes jitter in the image, which you don't want. And they also use power, and that means you have to adjust the power capabilities of the satellite in order to accommodate that. Then there are other problems involved with thermal infrared imaging, and the biggest one is the self emissions from the camera itself. And what I mean by that is uh, every element in the universe radiates in some way, and that radiation is a function of the temperature of what that object is, unless, of course, it's at 0 degrees absolute. The mirrors, lenses, struts, barrel, whatever you want to call it, of the camera are generally kept close to room temperature, even on orbit. And as such, they radiate thermal energy that's similar to the thermal energy that you're going to see when looking at the Earth. In that case, you have to find some way to subtract it out. Otherwise, you're going to be seeing extra energy that you're attributing to the ground. So trying to monitor what are called those self emissions. Some people call it false light, some people call it near field. That can be very difficult. It requires monitoring the temperature of all of the elements. It requires updating that information frequently. The temperatures normally change as a position in orbit relative to what's happened with the sun illuminating the outside or whether you're in darkness. All these things come into play and they make an infrared system much more complicated in many cases than just visible imagers.
That's interesting. That's a lot of system level requirements that a thermal payload expects from the satellite bus compared to the visible imaging payloads, right? Are there any other system level requirements that are required by a thermal payload in contrast to a multispectral or a panchromatic imaging payload, which is more common?
Well, as I said, you still have to monitor all the temperatures involved, and that includes the temperature of the focal plane that you're cooling, because as it turns out, uh, the response of the detectors generally change with the temperature. So you have to be careful about that. Um, Also, if we're talking about estimating land surface temperature, now you're not just talking about the satellite and the payload, you're talking about the processing to change from radiance that you're measuring by the system to land surface temperature. And that becomes even more complicated because in order to measure land surface temperature, you must correct for the atmospheric interference between the satellite and the ground. And in the thermal domain, unlike in the visible domain, you have what's called the emissivity of the ground. Emissivity of a ground target is a relationship between the uh, radiance that it gives off at a certain temperature to that of a perfect black body, which is easy to calculate. The problem is you don't know the emissivity of what you're looking at when you look at the ground. And from a strictly mathematical basis, when you try to solve for temperature, there are n equations to describe the system, but n plus 1 variables. And that means there's typically no unique solution for the land temperature. So in order to solve for temperature, you have to find some way of either estimating emissivity or narrowing down your estimate or looking it up in a database or having a human being look at the object and determining what it is and then looking it up in a database. Any number of things like that complicate the problem of trying to determine land surface temperature as a function of radiance.
So, the two big challenges, like you've just described, the first one is quantifying the thermal noise from other elements of the payload, or the other elements around the payload. That's the first challenge.
Yes.
And second one is processing of the thermal image as such, quantifying trying to filter out all the other information that gets overlaid onto these thermal images and trying to extract whatever value or whatever information that we want. So these are the two big challenges in handling thermal payloads. How difficult is it from an engineering perspective to overcome these challenges?
In theory, for most of these things, it's relatively straightforward. The problem comes in for the cost. How much is the mission willing to pay for things like that? And there's always a trade off in some respect relative to things like how many temperature thermistors are you going to have inside the camera to measure the different elements? Are you just going to approximate it? Or are you going to put thermistors on every element, every part of every element? All of that comes into play when you're trying to solve it. It's not, from an engineering standpoint, you can do it. The limitations come in from the design and cost aspect. And that's where you have to do a lot of analyses to determine your sensitivity to errors in each one of those. And that can be done, and it is done most of the time. Um, but other than that, it's very straightforward. Now, having said that, let me emphasize that the part about the emissivity is not so straightforward. There are a plethora of papers on how to determine land surface temperature when you don't know the emissivity. There are what are called temperature emissivity separation algorithms. There are various operational approaches. That is somewhat of an engineering problem, but it's more of a science problem and an operations problem than it is an engineering problem because there is no specific solution for that.
We actually had an episode of the thermal lens recorded on the land surface temperature and its challenges. So the audience might relate to a previous episode with Mike Perry to get some deep dive into that.
If I could take a little side trip here, I want to talk about something called calibration. Calibration has to be done for every system, and yet it's often the poor stepchild of remote sensing designs, um, especially for smaller systems. And it is extremely important for radiometry and for image quality and even geometric quality. And it's especially important for IR systems as opposed to visible systems. And a lot of people don't really understand the concept of calibration, but it is fairly simple. If I look at something that I know and I record a reading, and then I look at something unknown and get the same reading, I know that I'm looking at something that has the same characteristics as the thing that I looked at in the first place. And that first thing that I looked at, we call a calibrator. So we're comparing something that we don't know to something that we know. In visible systems, they'll very often use reflections of sunlight from various objects for calibration. That could be reflective panels, it could be the moon, it could be different areas on the ground where measurements are made. They can all be used as calibrators. IR systems are much more difficult to calibrate. Usually, high accuracy systems have a carefully characterized black body on board that they can set to different temperatures and form what's called a calibration curve, which means that for a variety of readings, I can get corrections over a variety of situations. But additionally, there are temperature measurements collected during calibration and imaging and other types of calibration of the lenses and the mirrors and the support structures to estimate the self-emissions that I spoke about earlier. Other less well-defined forms of calibration may be used, but they're inevitably the cause of greater errors. So you have different types of calibration that you have to do for the IR system. Then there's the issue of calibration frequency. Not only can temperatures change between readings, but I think I mentioned IR detectors tend to drift over time more than visible detectors. If the detector drifts, if its response drifts over time, then you don't know what you're seeing because it's changed since you looked at the calibrator. So any uncharacterized changes between the time of calibration, all of the calibrations that I mentioned, can result in radiometric error and image quality errors, and even sometimes geometric errors. In fact, there was one system I remember that had a fairly large F number, and when it was exposed to the sunlight in orbit, the barrel of the telescope underwent what we call hot dogging. In other words, it tended to bend a little bit because one side of the telescope would be hotter than the other, so it would bend away from the heat, which meant you were looking either at the side of the telescope or at some other portion of the ground that you didn't think you were looking at when you did the calibration. All of these things become a real problem.
Now that you mentioned the barrel of the telescope not behaving in a certain way and not having a black body on board, are the different components of the imaging system different for an IR system compared to the visible imaging system? And how difficult or easy is it to find these components or subsystems in the market?
Well, nowadays it's become relatively easy. There are certainly different components. Uh, the detectors that you use for thermal imaging are different than what are used in the visible system. Um, There are lots of different ones depending upon the exact wavelengths that you're looking at, uh, or any number of other things. I mentioned uncooled microbolometers earlier. Uh, they're off the shelf. In fact, I have an attachment for my cell phone that allows me to take thermal infrared video with a microbolometer. And I can even put the thermal image side by side with the camera from the cell phone. So that'll give you an idea of how inexpensive microbolometers can be. On the other hand, other detectors, there are what's called MERCAD, that stands for mercury cadmium telluride detectors. Um, they can be much more expensive. They can be tuned depending upon what mission you're looking at for different wavelengths, but they have to be cooled. And there, I won't go into some of the others. They get a little bit exotic after that. One of the other things you have to take into consideration are the lenses or mirrors. Lenses in thermal infrared systems are completely different than they are in visible systems. Typically, visible systems use lenses that are made of something like silica glass, and that cuts off at about 1 micron. So thermal infrared imagery or thermal infrared radiance doesn't penetrate ordinary glass. So you have to go to more exotic materials, such as sapphire or germanium or zinc selenide or zinc sulfide or any number of other very strange sounding materials that have to be ground into lenses. Having said that, they're commercially available. You can buy them almost anywhere in any size and any prescription. That's fairly easy to obtain. If you're using a mirror system, it gets somewhat easier because you're not worried about transmission as much as you worry about reflection. Um, so those are basically off the shelf. Um, but again, you end up with things like calibrators. Often calibrators uh, can be a little bit expensive, but again, you can buy them over the counter almost anywhere. Uh, but if you do, you have to find a way to be able to change the optics to look at the black body as opposed to looking at the ground. So that makes the optics a little bit more complicated. Having said that, it's not that difficult. Small missions or large missions for thermal infrared can both buy off the shelf components. There shouldn't be any problem. And in fact, that the idea of small satellites um, has become ubiquitous at this point. You can actually buy sensors for attitude determination or uh, acceleration that were originally designed for cell phones, but are now so small you can fit them into less than 1 square centimeter on your satellite bus. So the same technology that you're seeing in commercial systems on the ground has made its way into small satellites in orbit.
Yeah, maybe at this point it would be good to pan out a little bit and talk about radiometry in general, right? So Ellis, your group at Lockheed Martin was gave you the title of King of Radiometry, and
Do you have to include that?
yeah, absolutely, because I totally think it's apt given our discussion so far. You've explained a lot of really complex concepts to me in a very simple manner. But radiometry can be quite a broad term. So, what aspects of radiometry do you think users of IR data should know? And what concepts, what kind of technical details are they usually not aware of, but could greatly benefit from learning about?
Well, problem number one is most people do not know what radiometry is. They almost certainly don't know the difference between radiance and irradiance and radiant intensity or any number of other things that you can find relating things that are bright or not so bright. So that's problem number one. The way I like to explain radiance is imagine that you take a cardboard tube from the inside of a roll of paper towels and you hold that up to your eye and you stand 8 meters back from a whiteboard. And you'll look at it and you'll say, oh, I'm looking at this whiteboard. It's this bright. Now, if you walk to within 1 meter of that whiteboard and you look through the same paper tube, you're going to see the same brightness. Radiance only applies to large uniform areas. It doesn't apply to small things or points. For example, you can't measure radiance, and that's a particular term, of stars, because obviously the closer you get to a star, the brighter it's going to appear. So that's not radiance. That's radiant intensity, which is a little bit different. So number one, radiance is brightness that is for large uniform objects, and it doesn't matter how far away you are. That's number one. Number two, wavelength dependence is extremely important. Often people use a single value for radiance or irradiance in estimating performance, and that's almost always wrong, especially when the value is in terms of things like top of atmosphere solar irradiance, or worse, in foot candles, or something like that, or even black body radiation. Um, I've had a real problem with some requirements where they specify the system accuracy for temperature estimation for something on the ground, and then the contractor is given a requirement for temperature accuracy of a black body at the entrance to the camera, and they're completely different. And people don't really understand the difference. Even the manufacturers have trouble with that. So those are the two most important things they have to know about radiometry. It's what it is, and then it's wavelength dependent.
Okay, these are really good pointers. What skills are needed to work with thermal data? What kind of softwares? What kind of tools? Any programming languages? Of course, in addition to these technical concepts that you've mentioned.
I'm a little bit prejudiced here because my degrees are in physics, but I've worked as an engineer for decades. You really need a strong knowledge of the physics of thermal heat transfer and wave mechanics and optics. That's incredibly important. After all, this is an imaging system, so you have to understand that. And since it's thermal, you have to understand how heat gets transferred, whether it's radiative or conductive or convective. In addition, you have to know something about the characteristics of some detector components and satellite characteristics. It gets a little bit tricky to say exactly how much you have to know about each one, but if you consider the problems of estimating the temperature of the ground when you go through the atmosphere, that means you need to know a little bit about the atmosphere, how it affects radiance as a function of wavelength. Um, you also need to know something about at least the high level differences between, say, Mercad detectors and microbolometers and indium antimonide detectors, and what operating temperatures they work at because they're completely different. Um, those are the kinds of things you really need to know to work with thermal data. As far as tools, it depends upon what you're doing with the data. I happen to be a MATLAB person, but that's just me. Many people today like to work in Python. Um, I think it's a little bit easier to work in MATLAB, but I think Python is free, so that makes it a little bit easier to use. Um, there are also radiative transfer models you should be familiar with. Radiative transfer models, it sounds complicated. It's not. It's really a package that tells you basically the atmospheric effects between the ground and the sensor. So it will take into account things like the temperature of the air and the water vapor in the air and things like that. Uh, I basically had most of my experience with Modtran, which is commercially available sort of through the US Air Force, but throughout the world. There are several others out there. Uh, I believe there's one RTTOV that people can use. Whatever it is, you should be somewhat familiar with those kinds of models for atmospheric transfer functions. And as I said, modeling MATLAB, Python, There are any number of others. If you're working with thermal data and you're trying to exploit it as a user, that's a little bit different. As I said, users don't tend to know much about the design of these systems, uh, but they're still users. So they will often use packages like Envy, ENVI, if you're familiar with those. And there are others floating around.
Okay, and speaking from the perspective of a person working inside a mission, what do you see as differences between radiometry processing of the data in visible spectral range and the thermal spectral range? Is it similar or is it vastly different?
Well, as I mentioned, there's that problem of the knowledge of the self emissions from the optical system that's critical. That, of course, has to be removed from any readings. After that, everything becomes basically the same. Now we're talking about radiance in terms of radiometry and image quality. We're not talking about land surface temperature. Again, that's where you end up with atmospheric interference and things like that. After you get past the self emissions, things are very similar. You still have to know something about the response of the detectors. You still have to know the transmission through the telescope. In the visible system, that's typically expressed in signal to noise ratio. In thermal systems, it's a little bit different. Usually, you express that in terms of what's called noise equivalent delta temperature, which is a noise term. Otherwise, they're very similar.
Well, given the emergence of AI and machine learning, are these tools already affecting or going to affect thermal data processing, whether be it on board or on ground in any way?
I'm sure that machine learning will play a role. It already is playing a role. To be honest, I'm not a big fan of it. I think it's got its uses, but it worries me when people rely upon it too much without questioning it. Just as with any other system, it is subject to errors. And in my experience, we talk about type 1 and type 2 errors. Type 2 errors are what people would call false alarms, and type 1 errors are what we would call missed detections. So, for example, if you were going to use machine learning in an agricultural system and you wanted that agricultural system to automatically determine uh, how many crops you're looking at are wheat versus soybean, and it came back with a number and it said, oh, there are 6 wheat and 4 soybean. But you wouldn't know if that was correct. For all you knew, one of the wheat crops was a soybean crop. But it doesn't tell you that because it's using information that's internal to its processing itself, which is not obvious to the user. Now, that can be a problem, obviously, if you don't know what's going on. However, for other things, it can be very valuable. One of the big things I see as a use for it is things like automatic cloud detection. Cloud detection is difficult in and of itself, even for a human being who's looking at imagery. It can always be a problem. Some people will say, "Oh, there's a cloud over here." No, that's actually something else. Oh, well, that's a shadow over there from a cloud. No, it's actually a gray area of such and such. Because humans are subject to the same kinds of mistakes that machine learning is in terms of clouds, it's probably just as good, maybe better with machine learning to find clouds in an image and edit them out than it is to use human beings. Now, that's a great example. But if you rely upon it too much, it can be a real problem. So, uh, certainly you're going to be seeing it in ground processing. That's obvious. On board, I hesitate to do that because, at least in ground processing, you can go back and check on your own what's going on. For onboard processing, typically onboard processing is very good for limiting the amount of data that is sent down. As more and more systems collect more and more data, it gets harder to downlink that data quickly enough before the onboard memory becomes full or because your downlink rate is too slow. So for certain things, onboard processing can allow you to, for example, eliminate certain spectral bands that you may not need when you're downloading, which is great. Or it may allow you to compress to a higher degree for certain situations, thus allowing more data to come down. But at least you know what's going on in that case. If you use machine learning on board and it decides on its own what it's going to send down, you may have lost your opportunity to find out what exactly you're looking for is in there.
Not to mention the traceability.
Exactly. You just don't know.
Okay, so we covered many, many very interesting subjects and details. And just to wrap up, a bit of a broader question. How do you see, with all those developments, thermal remote sensing evolving in the future?
I would like to see hyperspectral thermal be brought up. It has so many possibilities that you could use for everything from atmospheric correction to, I mentioned, gas detection to giving you a better idea of land surface temperature or sea surface temperature. It helps with that n+1 versus n problem that I mentioned earlier. And I think they're going to get there. People started looking at this 20 some years ago. It never got anywhere, but with certain technologies becoming cheaper, more off the shelf, I think that's going to be the way to go with more and more spectral bands. It may not even be hyperspectral, it may just be multispectral. Certainly, we're using multispectral now. As for what you can do with it, I have high hopes of using other spectral bands such as midwave infrared instead of thermal infrared. I did a lot of work with midwave, and many people dismiss it because it's harder to process and get the correct answer with midwave. However, my early analyses said that in many instances it was as good or better than long wave infrared. The big advantage is that you get much better spatial resolution with midwave infrared. And some companies are trying to take advantage of that. Um, but if it's better spatial resolution, that gives you the opportunity to trade off ground sample distance, spatial resolution, against the size of the imager. So, for example, many systems today are working in the 50 to 100 meter range of resolution. For thermal, if you switch to midwave, you might be able to improve that by a factor of 3, or on the other hand, you might be able to reduce the volume of the imager by a factor of 3. Either way, I think that's a very important place to look.
Not to mention that the fact that they're less noisy than the long wave sensors, especially in the mercury cadmium telluride type.
It depends. I don't want to get into the details too much, but it depends upon what operating temperature you're at.
Fair enough.
They can also be noisy. Sometimes they can operate at the same temperatures, get the same noise. Sometimes they're colder. Not very often are they warmer, but it can happen. But yes, there are lots of trade offs, and I would think the future is there. I have seen airborne midwave, which is really, really good. And in fact, I know of a company that has actually, I think it's about 20 subsidiaries where they do everything from checking uh, building output, uh, thermal output in terms of leakage of heat, to trying to estimate the power output of a nuclear power plant based upon the temperature of the cooling ponds that they're using. So there are so many uses out there, and I think that's the future.
And it's coming. I mean, the NASA's mission Surface Biology and Geology is including midwave bands. So hopefully that's coming.
In addition to long wave,
Yes,
so they have to design that for the longest wavelength, no matter what. It just means that midwave will be better theoretically than the long wave.
possibly.
I was thinking just a single midwave system, but that's okay. Whatever they want to do, that's great.
Wonderful. Yeah, Ellis, this was more like a very, very engaging physics lesson, physics class to me. It was in a positive way. I don't mean I don't mean any other way, but yeah, you've explained a lot of these physics concepts, a lot of remote sensing concepts very succinctly. And if you are really going to put together a remote sensing course, even if it lasts 2 years, I'm definitely going to sign up for it.
Well, thank you. I doubt if I'll be able to, but I'll keep you in mind.
Well, thank you for taking time to talk to us. It was very, very informative.
You're welcome. It was fun.